Hi, my name is Sergey Levin, and today I'm going to talk about robotic learning. Recently at Google, we developed a robotic learning system that we call SEICAN, which allows a robot to carry out user instructions. So a user types what they want the robot to do, and the robot tries to understand this instruction, and then leverage a repertoire of learned skills that it can then deploy to try to carry out the user's command. So here it figures out that in order to do what the user asked, it needs to find a Coke can, it needs to pick it up, bring it to the trash, and then fetch a sponge, and so on. Now, this demonstration in many ways shows the state of the art of modern robotic learning. That you can get learning-based skills for rudimentary motor control, perception, you can combine it with language, and you can actually chain these skills in a kind of a hierarchical fashion to solve multi-stage tasks. But there's kind of a reason why there are certain things that this robot does, and certain other things that we omitted from this system. For example, the robot fetches the sponge, but it doesn't really make an attempt to clean it. It's not that it's impossible to clean the spill, but there's a reason why this was not one of the most readily low-hanging fruit for us to tackle. And that's really the topic of today's talk, is why is it there are certain things that are difficult for today's machines, and certain other things, perhaps counterintuitively, that appear to be easy. I'll start this story over 25 years ago with a major milestone in AI development, which was the match between Garry Kasparov and Deep Blue. This was the first match in which an AI system defeated a world champion at chess. But one of the things you might notice looking at this picture is that although the computer is playing chess, there's still a person on the other side of the board to actually move the pieces. If we fast forward 20 more years, the first computer to defeat a world champion at Go, this time using machine learning rather than search, was developed. But again, if we zoom the camera out, we can see that there's a person on the other side of the board who has to move the pieces. So why is that? Why is it that it was seemingly easier for us to develop algorithms that could win the game than it was to develop robots that could move the pieces? In fact, the history of AI is full of these kinds of counterintuitive milestones where time and time again we discover the things that we believe to be cognitively demanding tasks that are the purview of expert humans turn out to actually be quite feasible to automate, whereas other seemingly simple things turn out to be fiendishly difficult. So these are images generated by an image generation system called DALL-E, which takes a text string and then attempts to produce a picture that matches that string. So a user here typed a vibrant portrait painting of Salvador Dali, and the algorithm generated the picture. So again, this is the sort of thing that we associate with like fairly cognitively demanding tasks for humans. Typically we would consider creative art to be really the purview of human beings, but it seems like to some degree can actually be automated. In fact, this is a picture of Cosmopolitan magazine that was produced using this system. This is an AI-generated cover picture. When it comes to generating text, similar story, that large machine learning models can be used to produce text that not only looks like realistic text, but actually is responsive to user demands. So here this system was prompted to explain a joke. The joke is, did you see that Google just hired an eloquent whale for their TPU team? And the model explains the joke that TPUs are a type of computer chip, and a pod is a group of TPUs, which is also a group of whales. You can even get these things to hold a conversation. Here, the model on the left is pretending to be a cow and is telling jokes about going to Harvard. So these systems operate on a particular principle. They utilize large models and large amounts of data from the web. And by collecting this data and learning from it, they can solve problems that, to us appear like creative tasks, but, at some fundamental level have to do with synthesizing what they learn from massive internet experience. So where does that leave us with robots? Like, it kind of seems like we made a lot of advances. We can build chess-playing machines, we can build Go-playing machines, we can even generate pictures and text. Where are all the robotic housekeepers? Where are all the robot maids? Where are all the robot butlers? Why is it that we can solve seemingly cognitively demanding problems, but not what we might think of as fairly simple motor control tasks? Well, I'm going to tell you about several different robotic tasks and how they're solved traditionally and how they can be tackled with learning to hopefully paint a picture for you. Let's start with that problem of grasping the pieces. We might initially think that perhaps the problem is that it's just hard to build a robot that can pick up chess pieces or Go pieces, but that's really not the case. So this is a video from, at this point, about 15 years ago, demonstrating a robot called a PR1 cleaning up a house. And from this video, it's pretty apparent that physically, the robot has the ability to do most of the things that you need to tidy up a home. Now, the trick, of course, here is that the robot has a human brain. There's actually a person who's remote controlling this robot using a special interface, which means that this is only a test of the robot's physical hardware. So that's pretty nice. That means that we know that the hardware is not really the limiting factor. The problem is with the brain. If we can just build a better robot brain, of course, better hardware would help, but it doesn't seem to be the bottleneck. So let's talk about that problem of picking up the pieces. How do we get robots to pick things up traditionally? Well, classically, robotic grasping is really approached as a geometry problem. So you want to understand the shape of the thing in the environment, and then basically apply rudimentary physics to figure out where to put the fingers so that you will hold up that shape correctly. And that's the way that people have thought about this, and oftentimes you can apply techniques from 3D reconstruction, perception, planning, and so on, and basically solve this geometry problem. And the problem, of course, is that the geometry is just an abstraction of what's really going on in the real world. And the real world often violates this. So here's a video, for example, of a robot attempting to pick up some transparent bottles. The problem with transparent bottles is that even though they have geometry, it's very hard to deduce that geometry with depth sensors because the transparency fools the depth sensor. Other objects like socks, well, their geometry doesn't really matter that much. Their geometry, in fact, changes depending on how they're crumpled up. But also picking up socks is not that hard because if you just pinch them in the middle, you'll get it. The Go pieces, well, maybe they're small and slippery, so you might need to pick them up differently than if they were made of rubber, for example. The point is not that we just need to add more properties, like, yeah, if we account for whether it's rigid or soft, if we account for whether it's slippery or not, we'll do better. But the point is that the real world is much more complicated than the kind of abstractions that we might impose on it. So is there some way that we could solve this problem without having to manually understand and program each of these special properties? Well, maybe what we can do is we can get the robots to learn for themselves. Maybe instead of trying to get humans to explain how to pick things up, which is essentially what we're doing when we're programming geometry and material properties and so on, maybe we can get the robots to try it out and see what happens. This is an experiment that we did in 2016, where we set up something you can think of as a factory almost, but the purpose of this factory was not to manufacture goods, it was to collect data, to collect, in this case, experience of attempting to grasp objects. And by studying that experience, actual hands-on experience of actually attempting and failing to pick things up, we could use learning to build a system that can pick things up more successfully. But what was interesting about the system was not that it worked well, it was that the strategies it employed were very different from how hand-designed grasping systems function. So here I placed several different kinds of objects in front of the robot. I started with some rigid objects, and I'm intentionally picking things that are blue and roughly rectangular. First I had something large, then I had something smaller. Then I had this rectangular eraser, and you can see that for these objects, the robot adopts a pretty classical strategy. It puts the fingers on either side. It hesitates a little bit. It's trying to position them properly. But then I took this blue sponge, and you'll notice that the robot actually picks it up very differently. It sticks the finger right in the middle and pinches it. For this large, heavy object, it tries to find the center of mass because it knows that it needs to balance the object, otherwise it will slip out of the gripper. For this small object, it knows that it really needs to be flush against the table, so it really needs to get those little fingertips underneath it, otherwise it won't be able to pick it up. So the kind of strategies it develops are not purely geometrical. They're really paying a lot more attention to the different unique properties of these objects. In fact, we noticed that material properties were some of the first to emerge in the training process before it even understood anything about geometry. If we take this idea further, this is a successor to that system that was trained on more data and with more experience, then you get very interesting reactive policies where you can push something out of the gripper and it will attempt to recover. So besides just getting a system that works better, this autonomous learning procedure actually got a system that exhibits almost kind of human-like properties in how it behaves with physical objects. It doesn't treat grasping as a planning process or a passive perception process. It really treats it as an active decision-making process where there are recoveries, perturbations, and where all the different messy properties of the real world really matter. So that's what it means to learn from experience. You learn about the thing as it really is, not about the particular abstraction of that thing that is imposed on you by the programmer. So the resulting system works fairly well. Here's a demonstration in pretty dense clutter, and in fact for grasping from monocular cameras without depth sensing, this is actually one of the best systems in existence today. The same story holds in other domains. This is a robotic navigation experiment where we wanted to get this ground robot to drive through tall grass. Now, traditional methods for navigation employ sensors like LiDAR to detect obstacles in the environment and then navigate around those obstacles. So what you're seeing on the right-hand side is a visualization of the LiDAR reading from the onboard LiDAR, and you can see that those white dots represent obstacles that it thinks are in front of the robot. So it's going to keep turning and turning and turning until it thinks there are no obstacles in front of it, but of course it's in the middle of a grassy field, so the obstacles are everywhere. The trick is that the grass is not really an obstacle, right? You can drive straight through it, and if you had a proper understanding of navigational affordances, you could figure this out. So if you actually collect a lot of data of robots driving, plug that into a neural network, and get it to learn to predict whether a particular pattern of steering commands will result in collisions or whether it will result in a bumpy ride, and then optimize for steering commands that result in smooth collision-free navigation, then you can figure out that some things that look like obstacles are like grass are traversable, and some things like trees and walls aren't. And then you can actually put the robot in that grassy field and it will navigate properly. So what both of these examples illustrate is something called Moravec's paradox. This is the original statement from Hans Moravec. We are all prodigious Olympians in perceptual and motor areas, so good that we make the difficult look easy. Abstract thought, though, is a new trick, perhaps less than 100,000 years old. We have not yet mastered it. It is not all that intrinsically difficult, it just seems so when we do it. Here's a more modern interpretation by Steven Pinker. The main lesson of 35 years of AI research is that the hard problems are easy and the easy problems are hard. The mental abilities of a 4-year-old that we take for granted, recognizing a face, lifting a pencil, walking across a room, answering a question, in fact solve some of the hardest engineering problems ever conceived. So reflecting on the examples that I showed, you can kind of see how this fits in, that if we try to approach navigation or grasping as geometry problems, as problems where we have to engineer systems that can tackle them the way that we think they should be tackled, that turns out to be really difficult. The way that we can get traction on them is by learning to do them the way that humans do from experience. And this perhaps gives us some idea about why it's easier for us to build machines that can paint paintings and tell stories, because there's plenty of experience of paintings and stories on the web. There's not a lot of experience of robots picking up objects or navigating through grassy fields that you can get off the web. The reason that we want intelligent machines, and the reason that currently it's so hard to replace humans, is not because humans are particularly proficient in any one thing, it's because they're very flexible. For example, we can build software that'll allow an oil tanker to navigate halfway around the world pretty easily. But we still want a human crew on board because if something goes wrong and someone needs to go down to the engine room and fix some unexpected issue, that's what we need a person to do. So it's really that flexibility and adaptability that we need from learning-based machines. Imagine being stranded on a desert island and you have to survive, you have to build shelter, you have to find food. These are not necessarily tasks that you have to perform at superhuman proficiency, but you really have to get it right and you have to adapt to whatever the situation is that presents itself. So those of you that know the story of Robinson Crusoe, we find that story compelling not because Robinson Crusoe was very good at playing chess, but because it illustrates human ingenuity and adaptability, the resourcefulness that we exhibit when we're confronted with unfamiliar situations. And it's exactly this resourcefulness that requires us to put people on that oil tanker. We need something resourceful around to solve the unexpected problems. In principle, learning should be able to provide that for us, but of course, you don't get this sort of flexibility from mining lots of images from the web. One of the things you want is you want robots that can learn autonomously, right? Robinson Crusoe didn't get to try building the shelter 50 times and have some kind of magical reset in between those attempts that allowed him to try and try again. He had to exist in the world as it really is. Oftentimes when we approach robotic learning, we approach it as a kind of an episodic problem. So here you can see robots that are all learning to open doors, but something you'll notice that there's a person that comes along and closes the door between attempts to let them try again. More recently, my student Anusha Nagabandi developed a robotic learning system that could allow a robotic hand to manipulate multiple objects in the hand very dexterously. And we were very happy with this result, but of course we faced the same problem. It would drop these objects all the time and we need to pick them up again. So Anusha, being a good engineer, actually programmed a second robot that would reset the task so that the hand could try again. But of course, in the real world, this is not practical, right? If you want a robot that will actually go out into some environment, maybe it's going to be cleaning up your home and it fails at something, it needs to fix the situation on its own. One thing we could imagine doing is we can actually solve this issue by making the problem a bit harder. I'll illustrate this with an example. Let's say that you'd like a robot to make coffee by using a coffee machine. So you say, well, I'm going to train it to do a task. The task is put cup in coffee machine. If the robot attempts that task and fails, well, in the classic kind of setup, you would need a person to come along and fix this, put the cup back so that the robot can try again. But you don't want to have to do that. So what if you give the robot a second task? You say, well, if you messed up, try picking up the cup. So that's just a different task that you can practice. So if you fail task 1, do task 2. And if you succeed at task 1, maybe you replace the cup back. And if you fail at that and you spill the coffee, maybe that's a good opportunity to practice cleaning up a coffee spill. So instead of treating each mistake as something that requires intervention to allow you to try again, you treat each mistake as an opportunity to practice something new. Seemingly, you've made the problem harder because now the robot has to learn a lot more stuff, but now it can actually be easier because it can learn all this stuff on its own. Here's an example of an instantiation of this idea. Let's say we'd like a robot to learn to perform a dexterous in-hand manipulation task. A little simpler than that one with 2 balls, but similar idea. So we'd like it to reposition this object in the palm so that one of the spokes is always facing parallel to the palm, and it's located in the center. So this is a successful execution. We'll define a network of tasks, a graph, that includes picking up the object, repositioning it, putting it in the palm, flipping it upright, and so on, such that there's a closed graph, so from every position, there's some task available for the robot to practice. And if we do this, then we can actually run this entire training process fully automatically. So it takes the robot about 60 hours to learn how to do this, which is a pretty long time, but it's learning entirely from scratch. However, those 60 hours are fully automatic. So once we turn it on, the student who's running this experiment can go home and can do their homework and take a nap and so on, and come back a few days later and the robot has figured it out. Now, of course, this is a small-scale demonstration. We're still a long ways away from this to Robinson Crusoe, but hopefully this gives you some sense of how we can set up these fully embodied real-world learning systems to learn a little bit more the way that humans do. And the same idea can be applied in other domains. So here on the left, you can see a walking robot that learns how to run forward, run backward, and stand up if it falls, so they keep practicing. On the right is a robot that's trying to clean up the floor. And again, it picks up these objects, and then it can try again by putting the objects back down and kind of dirtying up the floor again so it can practice some more. Now, so far in all the systems I've showed you, the robots are not deciding on their own what to learn. The person still specifies the tasks for them, and they just have to go and learn how to do that task. But in general, of course, if we take the analogy of Robinson Crusoe further, you have to actually pick what kind of skills you're going to learn based on the needs of the situation, and also based on a degree of imagination and curiosity. So people, for example, do this all the time. When children are playing, they're not just moving their bodies around randomly. They're imagining hypothetical goals for themselves and then taking steps to achieve those goals. That's what a game essentially is. So can we get robots to play? Can we take this idea of embodied learning even further so that we have robots that not only autonomously learn tasks, but even autonomously decide which tasks they should be learning? So here I will actually tie this a little bit to some of these systems that generate pictures. See, current AI systems are actually very good at generating pictures, surprisingly perhaps. So maybe we can leverage that idea. Maybe we can say, if you have a robot that's in a particular environment and it needs to figure out what it should practice, perhaps it can imagine a potential situation that could happen in that environment, literally make up a picture, and then see if it can change the environment so that it matches that picture. This is basically leveraging the power of these image generation models in combination with robotic learning. Now, of course, the pictures here are going to be a lot simpler because these are much simpler environments, but here's an illustration of this in action. So we took this robotic arm and we put it in front of a cabinet with a door. Now, it's a little bit suggestive, of course, because, what do you do in this setting? Well, you open the door. We know this because we're people, because we know the semantics of this, but the robot doesn't know that. It just sees like a wooden box. So what is it going to do? It's going to reflect on its experience in this environment, which initially is nothing, and will imagine possible things that could happen. And then it will try to make those imagined things come true. So what you see in this picture in the top row are imagined pictures. These are not real photographs. These are images that the robot made up based on its experience. And what you see at the bottom is the robot moving the arm to try to make the real picture match the imagined one. So at 0 hours, it's pretty boring. At 0 hours, it doesn't really know how to do anything, so mostly just moves the arm around, forward and backward. After 5 or 10 hours, now it has accidentally opened the door a few times, so it knows that it should be imagining open doors quite a lot, because that's kind of interesting, that's unusual. So now it starts practicing to open the door, because it's already basically done. It's bored with just moving the arm. It wants to open the door, because that's the new thing, that's the unfamiliar thing. And further along, now it'll start opening the door to different angles, because it figured out, like, oh, this angle is pretty easy, now I'll try something a little different. And after 25 hours of this practicing process, it can actually open the door to any angle based on a user-specified goal. Now, this was the earliest prototype of the system, and it was pretty simple. So later on, we tried to extend this a little bit by incorporating another idea, which is basically, the reason that when you look at this picture, you know that opening the door is the interesting thing, that's because you have prior knowledge. You know something about doors. So can we give the robot a little bit of prior knowledge too? Can we basically give it lots of data of other tasks it solved before, and then we put it into some scene with some new objects, and we ask it to imagine possible things that it could do with these new objects by reflecting on its prior experience. And that can allow it to do much more sophisticated things. So here, prior experience includes moving lots of things around on the table, and then in the middle, we put it into a scene where there's this pot with a funny lid that has this like plastic thing attached to it. Now, it's never seen a lid like that, but it's seen lots of lids with other handles, so it can kind of imagine that maybe the lid goes on the pot. It'll also imagine other things, like it'll also imagine, well, maybe the lid just like goes off the table, or maybe the pot goes off the table. So it'll imagine crazy things as well, but among the things it imagines will also be some pretty useful things, and then we'll go start practicing all these things. And once it's practiced them, then we'll learn a lot more about how these particular objects work, augment its set of experience, and then it can carry out user-commanded goals. So here are a few more videos of this in action. This is set up as an experiment, so what you see in the top left is actually the final exam. The robot doesn't get to see this, we're just showing this to you. So we're saying, after the robot adapts to the scene, we'll ask it to pick up the shoe. And initially, if we were to test it before any adaptation, it would be pretty bad. It would succeed 12% of the time. The robot doesn't know that that's the test. Then in the lower left, you can see the training process. So here the robot imagines what it could do in this situation, and the shoe is like the new object, so it imagines picking up the shoe. And initially it's pretty bad, but then it gets a lot better over time. And then we administer the final exam, and it gets quite a lot better. Here's the same thing with that pot that I showed you before. So the final exam is going to be to put the lid on the pot, but again, the robot doesn't know this. This is just for your visualization. And then when the robot imagines goals, it'll do lots of useless stuff, but among that stuff, there will be many attempts to actually move the pot lid because it knows that lids tend to go on pots, even though this one has this really weird handle. Okay, now, so far I talked about very low-level behaviors, right? Moving objects around, picking things up. Now, we know that people can also do much more sophisticated things. And it's very tempting to think that techniques like reinforcement learning, what we call operant conditioning in biology, these are really for low-level behaviors. The high-level behaviors like planning, that's really the purview of symbolic reasoning, that's the purview of logic. Those are not things that you learn through trial and error. Or is that right? Well, this is what people used to think, right? So in this classic study by Wolfgang Kohler, a monkey was put in a room with a bunch of bananas hanging from the ceiling. And the monkey, being a fairly smart animal, sat around for a minute, thought about this, and then went and got some boxes, stacked up those boxes, and reached for the banana. And the scientists here said that, well, what the monkey was doing is it was planning. It was using its insight, its ability to do symbolic reasoning and logic to figure out how to solve this problem, unlike the lesser animals that are relegated to learning about the world through trial and error, like the robots I showed. But more recently, this is a study from 1984 by Epstein and colleagues. There's been some work that challenges this principle. So this experiment is sort of intentionally made to poke fun at the monkey study. But what Epstein and colleagues did is they took a pigeon and they put it in a box with a plastic banana hanging from the ceiling and a red box. Now, of course, pigeons have no desire to eat plastic bananas. They can also fly, and they don't need boxes to climb up to reach it. But this pigeon was primed with experience. It was trained to do certain things. It was trained not to fly. It was trained to stand on boxes. It was trained to pick up bananas. What it was not trained to do is to do all these things together. So the interesting conclusion of the study is that if you have the right repertoire of skills, which could be learned through trial and error, putting together those skills just kind of happens. So pigeons, they're not particularly prone to long horizon planning, and yet even a pigeon primed with these skills, not really having any particular reason to pick up bananas other than that it was trained to do that, figures out how to put the pieces together. So what I want to tell you about is a little experiment on how things that look a lot like planning and common sense can emerge from having the right experiential learning, from having the right trial and error learning. Imagine that you want to chop some onions. If you train a robot to do this, and it's very good at chopping onions, you put it in the kitchen, and maybe in this kitchen, you can chop onions, but you're in a lot of trouble for this robot because all it knows how to do is if it's holding a knife, chop the onion. It's not holding a knife right now, there's no onion in front of it, so even though they're somewhere in this kitchen, the robot will be completely lost for what to do. People don't suffer from this problem because people have common sense. You don't have a knife, fine. Check the drawers, it's going to be in one of the drawers. You don't have an onion, well, check the cabinets, check the pantry, there's probably an onion somewhere. So Let's think about how this kind of common sense can emerge without any planning, just from experience. If you learn how to chop an onion, then you can associate every state, every image that you see, with how good that state is for onion chopping. Basically, you can learn to predict, if I see this, will I succeed at chopping an onion? So obviously, like if you've got the knife on the onion right there, yeah, you're going to succeed. But you'll also learn that if you're holding a knife and there's an onion in front of you, you're going to succeed at chopping the onion because you're really good at it and you've succeeded every time in the past. So holding a knife is a very good thing for chopping onions. And that's very easy to figure out. That is not something that requires planning or insight or symbols. It just comes from experience. And now let's say that you have prior data of other things you've done. Basically prior experience from other things you've attempted to do, perhaps by inventing your own goals, perhaps by practicing, what have you. And some of it might involve picking up knives for other purposes, maybe for chopping a carrot. Well, you know that the state where you're holding a knife is a good state. So that means that any state you've seen before where you were holding a knife, even if it was for a very different reason, is also a good state. And any state that preceded that is also a good state because it led to a state where you're holding the knife. And that's how you can connect this up. Without any explicit planning, without symbols, you can figure out just based on what preceded what and what is good for the task, that opening a drawer is a really good idea if you want to chop an onion, because if you open a drawer, you know that that leads to states where you're holding a knife, and you know that states where you're holding a knife are good states. And you can back this all the way up. Of course, in reality, your prior data also includes other less useful things like making soup, cutting carrots, etc. So you have to know that some of these things are useful and some of them aren't. Some of them should be ignored and some shouldn't. But that's actually something that learning algorithms are very good at. And we can do this in practice. So here's an actual simulated experiment with a robot that is supposed to pick up a ball from an open drawer. So if all it gets to do is practice this drawer opening, ball picking task, then if the drawer is closed at test time, it won't know how to solve it. But if we give it past experience of other tasks like opening drawers, closing drawers, moving objects, where none of that prior experience actually involves picking up the ball, then this basic principle, this is called dynamic programming, can put together these concepts and figure out how to solve these problems. So then you get a robot that succeeds at picking up the ball from an open drawer. If the drawer is closed, it'll figure out that it should open it and pick up the ball, even though it's never seen those two things together, because it knows that opening the drawer leads to a state that is good for picking up the ball. If the top drawer is open, close the top drawer, open the bottom one, pick up the ball. If there's an obstruction, lift it out of the way, then open the drawer, then pick up the ball. Okay, so I covered a lot in this talk, but I want to bring us back to the Moravec's paradox, to this idea that the hard things are easy and the easy things are hard, that it's really the low-level motor control and perception that's really the challenge, and things that we associate with higher-level cognition, like playing chess and perhaps painting a painting, might not actually be all that hard from an engineering standpoint. So let's go back to some of those examples, like Garry Kasparov playing against Deep Blue or that cover of Cosmopolitan magazine. And let's think about how they were produced. So the Deep Blue system used search, very clever search methods, with massive compute to beat the world champion at chess. So the solution was solved with massive compute. AlphaGo used massive self-play, where a reinforcement learning algorithm played against itself for billions of games to solve the game of Go with massive compute. The image generation system was solved with massive compute and also massive data that you could mine from the web, because there's a lot of data on the internet of paintings, pictures, illustrations with corresponding text. So even though it might seem like a very complex creative problem, there are a lot of resources that you can throw at it to essentially brute force your way through this challenge. On the other hand, when we talk about embodied interaction, when we talk about picking up the pieces, so to speak, that's not something that's nearly as easy to brute force, because it's not really even the algorithms that are the challenge. Even the data itself is not readily available. So it's available to the child because the child spends the first few years of their life collecting that data. You can sort of think of the goal of childhood as data mining. We don't have sensory motor data of picking up objects on the internet. We have pictures of it, we have videos of it, but the sensory motor experience that we actually need to get robots to do this, that you have to go out and get on your own. And of course, it's unique to your own embodiment. And the kind of learning from experience and putting together that experience to solve novel problems, that's not something you get from looking at pictures on the internet. And it's also something that's very hard to get through massive compute, because it really lies at the intersection of the real world and the embodied agent. If you're relying on massive simulation, you don't have the real world. And if you're relying on data from the web, then you don't have the embodied agent. So perhaps the kind of autonomous robotic learning systems that I described can give us a way to approach this challenge, by actually interacting with the world directly, by learning more the way that humans do. But before I conclude, I want to leave you with one last thought. If the hard things are easy and the easy things are hard, then maybe solving those easy things can also help us solve the hard things. So in this talk, I focused a lot on low-level behaviors, picking up objects, navigating through tall grass. Of course, ultimately, we want robots to be able to do the more complex things too. We want them to actually go into the engine room of that oil tanker, figure out how to open the door, but also figure out how to actually repair the engine, which might be a complicated multi-step process. So why do I think that solving the easy things can help us solve the hard things? Well, at a high level, it's because that's kind of how it's worked before. So if we look at the history of deep learning, for example, for visual perception, initially people figured out that deep neural networks are very good at learning low-level features, features that are indicative of edges, corners, low-level visual properties. But then they figured out that the same algorithm that learns low-level features can actually just be applied at a larger scale to also learn higher level features. So if you make your network bigger, then we'll learn parts of faces, parts of cars, parts of elephants. You make it even bigger, it'll learn how to compose those parts and recognize what's going on in the scene, write narratives about it, and so on. So if you do a really good job of figuring out those low-level parts, you can just put more and more of them, and maybe you'll get the high-level parts. Now, that's not a fact, that's a guess, so I could be wrong about this. But maybe figuring out how to solve low-level tasks like picking up objects in the same manner that humans solve them through embodied experience could really give us a big leg up to solve the more complex tasks like building your robot housekeeper, a disaster relief robot that can rescue you from an earthquake, or a repair robot that can fix that engine in the oil tanker. Thank you very much for listening.